Welcome back, Physics 30. We'll look at the last section now for special relativity. If you turn to page 763, there's a couple of things we'll look at there. So, we'll look at this part. When do we use relativistic formulas? From a practical point of view, we do not have much opportunity in our daily lives to use math of relativity. For example, that gamma factor, 1 divided by the square root of 1 minus v squared over c squared, has a value of 1.005 when the speed that the traveling object is doing is 10% of the speed of light, or 0.10 c. Thus, for speeds even as high as 10% of the speed of light, which is 3.0 times 10 to the 7, the factor in relativistic formulas gives a numerical correction of less than 1%. For speeds less than 10% or unless mass and energy are interchanged, we don't usually need the more complicated relativistic formulas and can use the simple classical formulas. Okay, so again, as I mentioned previously, we're looking at huge velocities here, relatively close to that of the speed of light, to see huge differences. Okay, the last part, 26-11, the impact of special relativity. A great many experiments have been performed to test the predictions of special theory of relativity with an experimental error. No contradictions have been found. Scientists have therefore accepted relativity as an accurate description of nature. At speeds much less than that of the speed of light, as we saw, the relativistic formula is reduced to old classical ones, as we have discussed. So, when we're looking at really low speeds, the effect is somewhat negligible. We would, of course, hope, or rather insist, that this is true since Newtonian mechanics works so well for objects moving at less than the speed of light, so when the speeds are much, much less than c. This insistence on a more general theory, such as relativity, give the same results as the more restricted theory, such as the classical mechanics one, is called the Correspondence Principle. The two theories must correspond where their realms of validity overlap. Relativity thus does not contradict classical mechanics, rather it is a more general theory of which classical mechanics is now considered to be a limiting case. The importance of relativity is not simply that it gives more accurate results, especially at very high speeds. Much more than that, it's changed the way we view the world in terms of time and length contraction and other things that we unfortunately didn't get into. The concepts of space and time are now seen to be relative and intertwined with one another, whereas before they were considered absolute and separate. Even our concepts of matter and energy have changed. Either can be converted to the other. The impact of relativity extends far beyond physics. It has influenced other sciences and even the world of art and literature and general culture, as you see from many sci-fi movies that are, of course, in movie theaters, etc. The special theory of relativity we have studied deals with inertial reference frames only. And of course, the next thing we'll be looking at non-inertial frames and looking at the general theory of relativity, which of course, yes, deals with non-inertial frames. All right, we'll see you again.